So this is lecture number 30, which is on GPU parallelism. As we said, we'll have a whole module of lectures regarding GPU parallelism. So this is the first in that series. So now that this is the first time we're talking about GPUs, let's talk about why are we discussing GPUs in this course, especially the first time in a course like this. So I'm quoting Jensen Huang, who is the CEO of NVIDIA, and everybody I'm sure knows about NVIDIA because it's one of the hottest companies in the world these days in the tech world. So it goes like, GPU computing will become a time machine that lets you see the future, a spaceship that takes you to new worlds that are now within reach. And I mean, this is more or less true because most of the recent developments that are happening in deep learning, machine learning and artificial intelligence that's changing the world during our lifetimes is because of these hardware GPUs, okay? And most of them, the cutting edge hardware in GPU is being developed by NVIDIA. In fact, the book I'll be recommending to you is being written by NVIDIA experts because they are the ones who are developing these things in the first place. There's also a quotation from the book I'll be mentioning in the next page. Is NVIDIA is building a GPU supercomputer called Earth 2, and it's a digital twin of the whole planet Earth. They're partnering with the scientific community, of course, to predict the impact of today's action on the climate decades from now. Of course, people have been modeling, scientists have been modeling different processes on Earth, but developing a digital twin of Earth which simulates almost everything that happens on Earth in terms of the natural phenomena is phenomenal. Okay, and this is again being possible because of these GPUs. And some researcher said that because of your GPU, this was to NVIDIA, I can do my life's work in my lifetime. So that's what a scientist would love, is to be able to do whatever they wish in their lifetime, because most of the research that you tend to do will be converting to a wish list that people will achieve many years later. But hopefully with this, the rate at which computing power is increasing, particularly with the GPUs and the use cases which are possible with GPUs, many of the things that we never thought would actually be possible within our lifetimes. So this is the book we will be following. It's a book called Programming Massively Parallel Processors, a hands-on approach. So this is, I think, the 5th edition of the book, although the picture I've shown you is the 3rd edition. But anyways, this was published in 2022. So these are the 3 people, and the first 2 of these are, as I said, they are NVIDIA engineers who have been developing these technologies for the last few years. So you will know the actual stuff from the horse's mouth if you read this book, and that's the book we'll be following. So let's get into GPU parallelism. So till now we have been talking about CPU based parallelism, and again the use case of CPU based parallelism is still existing. I mean, it's not that once we talk about GPUs, CPU are not going to be useful at all. In fact, we'll do a comparison and show you, but there are some situations where CPUs reach a limitation, and that's one of those is the number of cores. I mean, if you think about it, the kind of cores, I mean, in terms of OpenMP, shared memory parallelism that we've been talking about, we typically go to 24 cores on a processor. If you put 2 processors on 2 sockets on a single motherboard, you end up getting 48. But that's sort of the maximum you would see in a typical HPC cluster. Although there are some machines like ARM based architecture and Ampere, which allows up to 192 cores on a single machine. But that is highly specialized architecture, and of course it's quite expensive as well, which allows 192 cores with a clock speed of 3.7 gigahertz. Very expensive, by the way. So in case you really want to use OpenMP with these kind of shared memory applications, you can buy this. But the point is, I mean, that's just 192 cores, and that's the limit because of the energy requirements of these hardware. So the question is, in case we require very large number of compute cores for doing some jobs, what do we do? So let's look at the NVIDIA V100 GPU cards that we have on our Param Himalaya supercomputer on the campus. So this has 5120 cores on one card. okay, and we have 2 cards on a single machine on the Param Himalaya supercomputer, and of course there are many of those computers available, so you can choose as many cards as you want. And V100 is not the latest one, by the way. So the latest NVIDIA GPU, that's called H100, allows 16,000 plus cores on a single card. So you see where we are heading. I mean, if you really want lots and lots of cores with some sort of shared memory, then and of course your use case matches with the kind of computing that can be done on a GPU, then you have to go in that direction. And that's the reason most of the deep learning, machine learning, neural networks basically based simulations happen on GPUs, because they are perfect for those kind of computations. In fact, over time the hardware industry is also evolving, so they are matching the hardware as per the software requirement. So let's compare the throughput, because we just don't want number of cores, we also want to make sure that the computation in terms of flops is also large, right. So let's look at the flops, or the floating point operations per second that these cards can give us. Are they actually, no, I mean, you can use as many cores as you want, but if the flops you get is lesser than CPUs, then why would you go for GPUs? Okay. So let's compare. So for this NVIDIA H100, which is the latest state of the art GPU available in the market, it has it gives you around 34 teraflops for a 64-bit double precision. So 64-bit is 8 bytes. So that's the double precision IEEE 754 standard we talk about. So that is 34 teraflops is what it can give. And now people typically they start going for single precision if you want a larger teraflop. So with single precision you get 67, that is FP32, this is basically 4 bytes. If you want to go for 16-bit half precision, you can get up to around 2000 teraflops. Now how does that compare to one of the latest CPUs available in the market, for example? So let's look at comparison with the Intel Core i9 13 generation that we have. So if you have 14 cores of a typical Intel i9, that will give you around 1 teraflop for an 8 byte precision. So that's 1 teraflop versus 34 teraflops. So there is a 30x difference in terms of the speed that we get from NVIDIA GPU card. So I mean, this is definitely faster. If it can give you 30x, then you would definitely want to go for it. In fact, if you go for if you go for FP32, that's 4 byte single precision, you have a speed up of 67 versus around 3 teraflops that you get in on a CPU. And CPUs typically don't even go for 16-bit half precision. But the point is that there is a huge difference. Again, it's not that every problem that runs on a CPU can run on a GPU effectively, but if it can, then you should definitely explore GPUs as compared to CPUs. So let's do a comparison, a very first level comparison. Of course, we'll go into details of the architecture of compute architecture as well as memory architecture in these systems in the GPUs, but let's do a first level comparison. So I've got 2 pictures. One is a typical CPU architecture that we have discussed till now, where you have a DRAM or a RAM, the main memory, then you have a cache, different levels of cache, then you have arithmetic logic units which do the calculations particularly for you, and then you have the control unit, which is whose job is to keep telling everyone what to do. Okay. And this is, I will discuss more about it, this is the architecture of a GPU. So CPUs are typically designed for low latency. Now if you remember the difference between latency and throughput. So latency is the time it takes to complete a given amount of job, and throughput is how much of a work can you do in a given amount of time. So if you have one CPU versus one GPU core, then CPU will be much faster because it is designed for low latency. It's designed for completing a unit amount of work in as quickly as possible. So typically you will see 4 gigahertz, so large clock cycles available on CPUs. You will have multiple levels of cache memories available, so that you can move the information closer to your core, and typically that results in large chip area and also large power required for running a given core. So this chip area is for a given core. Now let's compare that to a GPU. So GPUs are designed for throughput. So if you look at one GPU core, its clock cycle would be slow. You won't get up to 4 gigahertz with a GPU core. But the thing is that you will have lots of these cores available, lots and lots of. Okay. So if you have let's say in V100 we have 5,000 plus cores available, or 16,000 plus cores available in H100. So with lots of these cores we can get large throughput by parallelization, of course. So it is power efficient as compared to CPUs. So if your use case allows breaking the problem into very small basic computations, which does not require a high clock cycle, there's not a lot of serial stuff happening within one core, then you would typically go for a GPU. So you'll have very large number of floating point operations happening per second in the complete GPU, and you'll also have I mean we'll talk more about it, but the memory accesses is also much faster with the memories which are available on GPUs as such. So in general what happens is reducing latency is more expensive than increasing throughput. Okay. So if we have a CPU core and we'll want to make it much more faster, I mean you want to make CPUs much faster, then what you would do is you'll think of increasing the clock speed, right? That's basically you're saying that you want to reduce the latency by getting a lot more clock cycles. But what happens is that results in a lot more cost, and ultimately it's all about, everything ultimately boils down to cost. So if you are generating CPUs which are very expensive, then whatever job or whatever simulations you are doing with it will become so expensive that the cost of the product that you are going to make out of it will become so expensive that it will not make any sense to make that product at all. Okay. So increasing throughput proportionally rather than increasing latency is much easier with GPUs, hence we tend to go for GPUs. In fact, the memory bandwidth in GPUs is 10 times more as compared to CPUs. So memory bandwidth is the number of cycles you need to do a given amount of floating point operation, for example. So remember, we had to bring in information from the main memory to your arithmetic logic unit in a CPU. So memory bandwidth is the cost associated, the number of cycles you need to bring the information to your CPU to be able to do any useful calculation with those numbers. So that number of cycles required to move information from the memory of a GPU to its cores is 10 times faster as compared to a typical CPU. And that again, I mean remember, it's all about, sometimes we feel that it's just about the power or the speed of computation, but sometimes it all boils down to the rate at which you can access memory. So that also is important. In fact, we will talk about use cases or situations where you will be able to calculate and see whether the bottleneck with a GPU based computation is actually the memory data transfer, or whether the bottleneck is because of the computational power. Sometimes the computational power is available, but the data has to be moved, and that takes in much more time than the compute core would require. So we will do some rough calculations to figure out those situations as well. So let's very quickly look at the architecture of a GPU. So you see that you have a DRAM or a dynamic RAM, just like you have in your main memory, you have a RAM. In GPU cards, you also have a RAM. So when you buy a GPU card, it says 8 gigabyte or 16 gigabyte or 32 gigabyte. If you're getting rich, you'll go for those 32 gigs card or more. So that is, and that actually increases the cost tremendously in a GPU. So that DRAM available on a GPU is is separate from CPU. You will not access CPU's RAM for doing calculations on a GPU. So you have to move information to a GPU RAM and then do calculations with it. And we'll talk more about it. We'll writing a code today using CUDA. We'll discuss more about that later in today's class. So you see that you have a DRAM, and so this orange is basically your memory. Thanks. So this orange part is the memory that you have here, and you can see that and the yellow is the control unit. So that's required that basically controls the what work you would want to do, what work has to be given to a given core. So we can see here that there are lots of these green units which are the compute units or the cores, GPU cores that you have, and there are groups of these green units which have an orange and a yellow unit with it. So this orange is the memory. So there is some shared memory available for a collection of cores that's much faster, and then you also have some other levels of memories available which are common for all the cores available on GPU. So there is a lot of the architecture is very different from a CPU, and that is the reason it's not possible to simply use the same code that we had written on a CPU on a GPU. Okay, so GPU's architecture is different, so the way we program it, if you want to do a first level program, yes, there will be frameworks available which allow you to do that, but if you want to make it optimized, you have to again understand the architecture, and the architecture also changes with time. The GPU architecture has been evolving over the last few years, where different, this is not a general standard GPU architecture. This is just one for illustration purposes, but as we will see in the next few lectures, when you talk about the compute and the memory architectures of GPU, they have been changing. There are different kinds of cores like tensor cores available now on GPUs and so on. So one has to understand that to be able to write code which is optimized. So what are the typical applications or use cases that you will have with GPUs? So typically if you have large number of very light calculations, you will want to go for GPUs. Okay, so they are, why were GPUs actually developed? So GPUs were initially developed for the gaming industry. Okay, when you play games, you want to have a high number of frames per second so that the game looks realistic. And of course you are interacting with the game, but you would want to see on a huge screen and very large resolution, very large FPS, so that if you're driving a car and you suddenly take a turn, then you should be able to see that effect on the screen. It's not that although the processing happened, but you did not see a collision happening, so it does not look as real. So for that, what you need to do is, if you have a very large resolution, that basically means you have lots and lots of pixels on the screen, and these pixels have to be populated in terms of value. As to, for a given visual representation, you have to calculate these pixel values so that they can be then shown on the screen. So calculating the pixel value is some mathematical operation, and you have to do lots and lots of these operations on many pixels for that high resolution, and you have to do it for a large frames per second. So you have to do them very quickly. So this was the actual use case of graphical processing units or the GPUs. But then of course scientists keep coming up with amazing ideas. So when they were thinking, when the GPU industry, GPUs were growing for the gaming industry, they realized that it's all about cost, right? So when very good GPUs were being developed by NVIDIA and other companies like AMD, So what happened was that the cost started reducing because the number of buyers in the market was huge. So when the cost goes down, people thought that maybe we can do the computing, scientific computing on these GPUs more cost effectively as compared to doing that on a CPU, because CPUs, the high-end CPUs, were still developed for these supercomputers or clusters, so the cost was quite high, still very high. So that is where people started exploring, or they started developing programming languages to do these scientific computations, more general purpose computations as compared to these specific pixel based calculations for scientific computing exercises. And that is the reason we are talking about GPUs in this course. So applications like machine learning, deep learning, basically neural networks goes along really well with GPUs. Molecular dynamics, which is getting the which is forming the foundation of drug discovery. So computational biology, computational chemistry, computational physics. So molecular dynamics is also very efficient when done on GPUs. Financial modeling, I mean, is also being done. Image processing, of course, that's what it was developed for. I mean, advanced algorithms of image processing are also being implemented on GPUs. Now, as I said that CPU algorithms which are efficient in general on CPUs may not run as well on GPUs. So, it's again, CPUs are for low latency, GPUs are for high throughput. So, I mean, what do we do? I mean, there are situations where some part of the program has a sequential part, right? And there you would want a low latency kind of a setup. And there are some situations which are highly parallelized with very light calculations. So that is where you can harness the power of GPUs. So this is where the idea of heterogeneous parallelism comes. In fact, sometimes you will see that GPU based computing is also called heterogeneous computing. In fact, the course is called Introduction to Heterogeneous Computing. So that's basically GPUs. So GPUs, I mean, you will never have a program that is completely running everything from the initial to the end on a GPU. There are parts of the program which run on CPUs, and there are parts of the program that run on GPUs. And it takes a very good understanding of parallelization to be able to write such programs. But people run these parts of programs on CPUs, and these are those parts which are sequential in nature. Okay, so you will have one machine on which you have a couple of GPU cards installed, but there are situations where you have a sequential part which requires a low latency demand. So you will run that part on your CPU in more or less a sequential manner. So you have a CPU that gives 4.8 gigahertz, for example. So you'll use that for running the sequential part, and as soon as you reach a parallel part, you generate GPU threads and run them on the GPU, and when that is done, you come back to the CPU and run the sequential part. So we are still not talking about running the CPU part in a parallelized fashion as well. We are talking about CPU in the sequential sense and GPU in the parallelized sense. So there is still a lot of scope of developing programs which are parallelized both on CPUs and GPUs. But the heterogeneous parallelism that I talk about here in this slide, and that you will see in GPUs in general, will talk about running the CPU part in sequential sense and GPU part in the parallelized sense. In fact, you will also see that use of GPUs for computing is sometimes known as accelerating your computing or program, and GPUs are called accelerators. Okay. So again, the idea is that you have a CPU based program, sequential program, but you identified that there were highly parallelized sections in your program, like loops and so on, that you could potentially run on GPUs. So you somehow wrote code directives, or you ported that to a GPU, and then you brought back the results from GPU and proceeded further in the sequential CPU fashion. So that's the reason we call them accelerators, because they are used to accelerate the program whenever possible. But there are other kinds of accelerators also possible, like FPGAs and all, but we will not go there. That's not the aim of this course. This module, it's all about GPUs. So now that we have some understanding of the architecture of a GPU and how that differentiates from a CPU architecture, and we also have some understanding of when does it make sense to use GPUs, let's talk about some sort of historical discussion on the development of GPU computing. Okay. So, the programming languages or the programs or the frameworks that were developed or that exist even till today, which are used these days for programming GPUs. So, when we talk about doing computing on GPUs, we are talking about GPU. So, that is general purpose computing on a GPU, because GPUs were designed for video edit for gaming industry, for calculating the pixel values. Okay. So, scientists thought about doing general purpose computing on GPUs. So, for these GPU programming, people wrote application programming interfaces, APIs, to do the calculations. But see, under the hood, it was all developed for pixel based calculations initially, back in those days. So, these APIs were very complex because you had to visualize your computation in the form of some pixel calculations. So, that was unnecessary, but that is the only way possible, because the initial programming language was developed for pixel calculations. So, everything, I mean, every code that you write has to be expressed as if you are painting pixels. Okay. So, these APIs were available for painting pixels, but you had to figure out how your calculation can be used, how can you use those API function calls for expressing your computations. So, it was too complicated to work with, but of course, that was the only way possible. So, that is how things worked. Then NVIDIA in 2007 came up with a programming language or a framework called CUDA, that is called Compute Unified Device Architecture. And I am sure whoever does gaming with an NVIDIA card, you would have seen CUDA being installed or updated on your computer now and then. So, this programming framework called CUDA, which provided extensions for C, C++ and Fortran, which still provides, of course, this supported or supports CPU GPU execution. So, the same heterogeneous parallelism I talked about. So, you have a C code or a C++ code or a Fortran code that is written for a sequential nature, but whenever you feel that there are possibilities for doing those calculations on a GPU like OpenMP, but slightly more complicated, then you would modify the program in such a way so that those highly data parallel jobs can be run on the GPUs. And the good thing about, and the reason CUDA has really caught up is because it was developed by the same company that was making hardware, NVIDIA. And that is really useful, because you see that if while developing software changes, they realize that what if the hardware was like this, we could do our programming much faster. Well, that is good, because you can do it, you own the hardware as well. So, you can do the experiments, you can come up with the next level of hardware which allow you to do things which your software can also do more efficiently. It is like Apple, you know, Apple has come up with its own architecture now, the Apple Silicon. It used to use Intel architecture earlier, many years ago. Well, not many years ago, but maybe 5 or 6 or 7 years ago, used to get Intel processor and Intel architecture on an Apple Mac machine. But now they have stopped using Intel, they completely use Apple Silicon, M4 these days, M4 chips. So, the reason they did that was because they have Mac OS, it's their own software OS that runs on their own hardware. So, they can really control things, and that is the reason with a modest amount of resource, Apples are typically much faster than other hardware that's available in the market. Okay, of course, I mean they're beautiful as well, but they're quite optimized in that sense. So the same thing holds for NVIDIA as well, and that is the reason they have almost significant amount of market share when it comes to GPUs these days. And whoever had bought NVIDIA stocks 2 or 3 years ago, they have been very happy. By the way, 2 years ago in my class I mentioned, so is there in some video that you should definitely go for NVIDIA, and so from 2 years ago to today NVIDIA stocks have increased a lot. Of course, you cannot invest in NVIDIA in India, you have to have some relative who can do it on your behalf but I mean I'm telling it again today, they're still in business although the market is fluctuating. But the point is that GPUs, I mean think in terms of the user's perspective. If everybody wants to use NVIDIA, then definitely the company is doing really well. Now let's come back to the technical part. So this was CUDA, but then what happened was many other realized that what about other hardware? Can we have something that allows us to write to use APIs for hardware which are not NVIDIA? Okay, so let's have some democratization of programming language in such a way so that we can access other hardware as well, and that is where OpenCL came. So there is this group called Kronos group, which includes Apple, Intel, AMD, NVIDIA of course as well, Microsoft and some other companies in the semiconductor industry. They came up with this language called a programming language called OpenCL, which is cross-platform in the sense that it can work with other hardware as well. So it's very similar. So if you understand CUDA, you can understand OpenCL and vice versa. So it's very similar. The extensions and the APIs are quite similar in that sense. And then we have something called OpenACC. So if you are a fan of OpenMP, where you simply put directives, like a couple of directives around loops, and things start working much faster, that is also possible. And we'll have one full lecture on OpenACC where we will have a look at some programs which we'll run on Param Himalaya, by the way, because they have OpenACC available there, and really see how much fast you can make a program by running them on a good GPU with just a few amount of program lines. And then if you prefer Python, which many of us do, you have modules like CuPy, Numba, CUDA-JIT, then PyTorch, TensorFlow. So I'll demonstrate these. I mean, this is very easy to understand if you understand the general CUDA language, but I will definitely demonstrate these in the class if possible. So let's get into CUDA, okay? Because if you understand how to work with CUDA, you will more or less understand this GPU parallelism in general. And in this course, we will talk about CUDA C as compared to CUDA Fortran, because CUDA C is more popular. And again, the aim of this discussion will not be able to write C or Fortran, CUDA C programs from scratch. You should not get stuck on the syntax. You should focus more on the ideas of parallelism, GPU parallelism that we are talking about. Okay. So in CUDA, while writing GPU codes in this heterogeneous parallelism approach, you have two kinds of codes. One is a host code, the other is a device code. Host code is, the host is your CPU, and device is your GPU. So host code caters to the program that runs on your CPU, and device code is the code that runs on your GPU. So they have to be clearly different. So if you see in the figure, you start with a serial code, then you reach a situation where you think you can parallelize. So that is where you have your device code. So device code has functions which are known as kernels, just a terminology. So we will be using the word kernels as compared to functions. These kernels or the kernel functions, they run on a GPU, and GPU has lots of cores available. Okay, so for each core, very loosely speaking, you will have a thread. So thread, remember, is that independent amount of work that can be done. So you generate lots of threads, and each thread will execute that kernel or a kernel function on a GPU. So basically you have some functions called kernel functions which run on all the threads on GPUs. Okay. So this is a kernel function call. I mean, we'll discuss more about it, so don't worry about the syntax as such. And when that job is done, you again come back to your CPU serial code, and then when you again realize that you have reached a stage where you want to launch more threads, so you launch more threads, or you sometimes called we launch a grid. Again, these are terms, okay, but you need to understand that. So we say that this program that I have shown you, it launches or it generates grids twice. So generating or launching a grid means you launch lots of threads. So grid is basically that has all the threads in a GPU. Okay. Now if you look at this program, it seems that first in time CPU runs, then you reach a part, then GPU runs, then CPU runs, but that is how we will discuss the initial or the basic programs that we discussed in these 5 or 6 lectures. But you can also have situation where CPU and GPU are working in parallel at the same time, so they are overlapping in time. That is also possible. Okay. So as and when you come to these more advanced ideas, things become more complex. But of course, the aim of this course is to get you started, and then you can get into the details of these ideas as much as possible. But yes, it is possible to have CPUs and GPUs working at the same time in a CUDA program. But that is not what we will discuss. We will discuss CPU working sequentially, then you have a GPU part which works in parallel, then you again have a CPU part working sequentially, and so on. Right, so let us get into business. Let us look at a program which is sort of a hello world in CUDA. We will develop this program. Again, this is available in the book that I had shared. So we will develop a program slowly, so that we understand each and every aspect of the program, because there is some new approach happening here. So you will see variables. Again, don't get stressed about the syntax, just focus on what I am explaining. So if you see, so people at the back, can you read the code? Somebody at the back? Yes, okay, thank you. So you see variables which have an underscore h. So this is for host, because remember, host is your CPU. So your CPU memory is your RAM, the main memory, the RAM that you have inserted in your motherboard. Then you have a GPU which has its own RAM, the DRAM, which is what you get in a GPU card. So they are different. Okay. So when I say a underscore h, that is in this case it's an array or a vector that is sitting on your host memory, which is your main memory on a CPU, with this available with CPU. And if you have underscore d or d underscore, that's a convention. Those are variables which are sitting on your GPU memory. Okay. So this is how a traditional code would look. This is not parallelized using GPU till now. So there will be a main function which simply calls a function called vector add. It passes two vectors a and b which are supposed to be added. It also passes a vector c which will contain the result of a plus b, and then it passes the number of elements in the vectors. And then you have a function vector add which takes in these 4 arguments, where the first 3 are type float, or as we call double in Fortran, and well, actually this is float. well, not double, but that's okay. So these are real numbers, and then you have an integer n, and you have a for loop which iterates over all the elements of the arrays A and B, and it adds the ith element of A to the ith element of B and stores that into the ith element of C. Okay. So that's a traditional program, not parallelized with GPU till now. But how would that work on a CUDA? So on CUDA, you have three parts in a program. Part 1 is where the memory allocation happens. So on your device, that's on the GPU card, which has a DRAM, you allocate space there. Okay. So once you have allocated enough space on the GPU card, now you have to copy the arrays or the vectors A and B from your CPU memory to your GPU memory. So that's where you copy, because your arrays exist on a CPU, your main memory. That's where everything is initialized, and then that has to be copied to your GPU. So that is part 1. Now once the information is available on a GPU memory or a device memory, you launch threads on the GPU, and after launching threads you do calculations. Of course that happens at the same time. So you create lots of threads, and these threads go on your GPU cores, and the calculation happens there. So once you have done the calculations, your GPU or the device memory is updated now with the actual values of A plus B. So the vector C available on your device memory is holding the right values, but you have to bring it back from your GPU to your CPU memory or the main memory to be able to do anything with it. If you want to print it on the screen, you want to send it to a file, whatever. So now in part 3, you copy the vector C from device to your host. Host memory is your the memory, the RAM available on your motherboard, and you free the device memory, because the device memory is not needed anymore, so you have to free it. Otherwise, if you try to use it again, it says CUDA out of memory, and whoever has done machine learning is scared of this CUDA out of memory. Okay. Is that clear? So when I say allocate memory, I'm talking about this memory on the device. Okay, this DRAM on the GPU is where you allocate, not the orange parts available in the which are closer to your cores. We're talking about this DRAM where you allocate memory on the device. So what we'll do is we'll talk about parts 1 and 3 first, and then we'll go to part 2. So part 1 and 3 is much easier. You have to allocate some memory, you have to copy the data from host to device, and then part 3 is to copy the data from device back to host and free the memory on the device. So let's look at the program for that. Again, don't worry about the syntax, just understand the logic here. So you have this function again called vector add, vec_add, which takes in A, B and C. Now this function will be executed on the host, on the CPU. So these A, B and C exist on the host and also pass an integer n. So now you want to allocate some memory on device, because device memory is all available now. So to allocate the memory, you have to understand how much memory has to be allocated. So you calculate the size. Is a variable integer called size, which calculates the number of bytes required to be allocated. So n is the number of elements in the vector, and float has some size. So let's say 4 bytes. So size of float will return 4 bytes. So 4 bytes times n will be the total amount of memory required for one vector or an array. Okay. And then you have to, these are pointers, but again don't worry about that. So A underscore D will refer to the array on the device. B underscore D will refer to the array B on the device. So A underscore D is different from A underscore H. A underscore H is the array that is sitting on the host memory, and A underscore D is the array sitting on the device memory. So you have a function called CUDA malloc, okay, which does memory allocation, as the name suggests, on CUDA memory or on GPU memory. So what you have to pass to this function, again don't worry about the strange syntax. If I had written this code in Fortran, things would have been much easier for you to understand, but because CUDA C is much more popular than CUDA Fortran, I did not want to. It's much easier for me to find codes on CUDA C firstly, and it's much easier for me to for you to be able to use these ideas if you write your own program, which will in most cases will be on CUDA C. So you have to pass the name of the variable, which is A underscore D, and the size. So if you pass these two things to a function called CUDA malloc, it figures out, it already knows, your program knows what is the GPU available, where is it sitting on the motherboard, and so on. If you have only one, if you have multiple GPU cards, you have to figure out, you have to set some variable to a value which is equal to the GPU card number. But here we don't worry about that, we are assuming there is only one GPU card available on your machine. So once you allocate these memories for A underscore D, B underscore D, and C underscore D, now the memory is being allocated on the GPU memory. Now allocation is done, but you have to copy the information now from your CPU memory to your device memory. So for that you have a function called CUDA mem copy, CUDA mem cpy, and what do you have to pass to it? You have to pass to it the device location of the variable A, that is A underscore D, the host location of A underscore H on the host memory, the size of these arrays, and what operation you want to do. Do you want to copy from host to device or device to host? So in this case you pass in a constant called CUDA mem copy host to device. So this knows that this variable A underscore H has to be copied to A underscore D, and at the end in part 3 you will have CUDA mem copy device to host. So that is where you will copy the device variable. If you make a mistake here, what happens is you end up copying the host values which were 0 again back to device. So that does not do the intended job. Okay. So part 1 is to allocate memory on your device, copy the information or the memory or the array from your host to device. Part 3 is where you copy the information back from device to host, and then you have to free the memory on the device, because device has very limited memory, sometimes around 8 gigabytes. If you don't free it, you cannot use it again. So you have this function called CUDA free. Simply you pass on the variable of the device, and it frees the memory associated with that variable. All these 3 arrays are free now. Is that clear? Just one word of caution: you should never try to access your device memory from a host program. That can crash your program, because when you have the host part of the program, if you try to use A underscore D, B underscore D, or C underscore D here, it will really get confused, because A underscore D exists on a memory that is on a GPU card, but this host program is running on the CPU. So don't try to dereference the pointers of the device, or don't try to access the device arrays on a CPU code. They are intended to be used on the kernel functions which are executed on GPUs, and that we will discuss in the lecture tomorrow when we start talking about part 2, which does the computation. Okay. So we will stop this lecture here now, and we will proceed further from here tomorrow. If you